Today we will go over hydrocarbons. Organic chemistry is the study of compounds that contain carbons, and hydrocarbon is one of the most important concepts of organic chemistry to learn. And this will be separated into two parts. And this will be part one. Okay, so let's start. So, first, before going over hydrocarbon, we need to understand why carbon. Why carbon is so important to study that there is a field called organic chemistry. So, carbon is unique in many ways compared to other elements. Carbon is allowed to form four covalent bonds with its characteristics of having four valence electrons. In addition, it can also form single, double, and triple bonds. These characteristics of four bonds and double, triple, single bonds allow for great diversity of carbon containing compounds. And this is the reason why carbon is one of the most frequent elements in many compounds that we have seen after hydrogens. Carbon also has a tendency to catenate, meaning it can form chains or rings from itself. Uh, you can see the example below. Other elements like silicon can form chains as well, but it is not as stable as the carbon chain because they have different different they have because silicon has greater difference in each bond strength than the carbon. So for example, silicon and oxygen bond is much stronger than silicon bond. So there's not equal there isn't equal or similar balance between them. However, carbon oxygen and carbon carbon is almost equal in strength with difference of only 12 kJ per mole. And this allows for carbon chain to be much more stable and also exist peacefully in the oxygen-rich environment. And that is why carbon is more frequent than silicon most of the time. Okay, so now let's go over what hydrocarbon means. Hydrocarbons are compounds that contain only hydrogens and carbons. Therefore, molecules like glucose, which has formula of C6H12O6, are not hydrocarbons because they contain oxygen. Hydrocarbons contain only hydrogens and carbons. Hydrocarbons can be separated into two types: aliphatic hydrocarbons and aromatic hydrocarbons. Aliphatic hydrocarbons are those that form chain of carbons and hydrogens, and while aromatic hydrocarbons are those that form rings of carbons and hydrogens. You can refer to the image on the right for a greater understanding. Aliphatic hydrocarbons can also be categorized further into alkanes, alkenes, and alkynes. Alkanes are carbon chains with only single bonds. Alkenes Alkenes are those with double bonds, and alkynes with triple bonds. The picture on the right also displays examples of alkanes, alkenes, and alkynes. You can see that ethane, which is example of alkanes, have only single bonds. Ethene, which is example of alkenes, have double bonds, and ethine, which has triple bonds similar to alkynes. The name can get somewhat more confusing if both double, triple bonds are present, but we will go over that in later sections of other lectures. It might be in part 2 or the next video. Hydrocarbons can have multiple structures despite having the same formula, and we call them structural isomers. For example, butane and isobutane have same uh, molecular formula of C4H10. However, we're able to observe through the structural formula that the molecule is completely different in the structure. This is common as carbon has a characteristic to form multiple bonds, a total of four, maximum of four, and the results of different structural isomers result in completely different molecules with completely different characteristics. Butane here has two structural isomers, and other hydrocarbons have multiple structural isomers as well. For instance, pentane has three, hexane has five, and decane has 75 structural isomers. A stereoisomer is also an important concept of hydrocarbons to go over. Stereoisomers are molecules that have same molecular formula and sequences of bonded atoms, but different in three-dimensional orientation of atoms. A stereoisomer can be separated into two categories: geometric isomers and optical isomers. Geometric isomers, or also known as cis-trans isomers, are isomers that are different due to the rotation in double bond. In the top right picture, you're able to observe that chlorine and bromine are in different side, uh, although the molecular formula is equal. This is an example of geometric isomer, and it is only possible in double bonds due to its characteristic of rotation. In single bond, the carbon-carbon single bond is free to rotate. Thus, it does not matter with where chlorine and bromine is located, because it will be constantly rotating, and it will be equal at the end. However, in double bond, the bond is rigid and cannot rotate, resulting in different types of molecules like this. The other type of stereoisomer, which is optical isomer, is more involved in three-dimensional orientation. Optical isomers, or also known as enantiomers, are two molecules that are non-superimposable mirror images of one another, meaning they are a reflection of each other when faced with the mirror. The image in the image on the bottom right shows an example of optical isomer. Molecules that exhibit optical isomerism are said to be chiral. So chiral is like the adjective version of optical isomerism. And optical isomers, or those chiral molecules, are important in other fields like biology, as they influence the reaction caused by enzymes and such. Therefore, many biological molecules are chiral, following only specific reactions with specific enzymes. In the next part, we will go over more about nomenclature and go more depth into alkanes, alkynes. But this is for the part one. This is the end of our lecture video, and thank you for listening.